Hi, everyone. I hope you're doing well. And let's go ahead and dive into the subject of global climate change. And this is going to be the first of three lectures that we're going to have on this subject. And this is kind of what we've been building up to for the entire semester. Uh, this is a science class for non-science majors, so we started off with an introduction to science. Uh, we then talked about biology because this is a class in the biology department, the biology curriculum. And humans are biological organisms, and we have an impact on the ecosystems in which we live. And then we looked at the various kinds of resources available to us and how we're consuming them. And so now we're going to start trying to put it all together as we move towards the end of the semester and talk about one of the largest impacts that humans are having on the earth right now. Now, some of you may not necessarily subscribe to that interpretation, and that's absolutely fine because we're going to talk about that. There are arguments that there are other things affecting global climate. We're going to look at some of those. The key is going to be, and I will be hitting this repeatedly, the key is going to be, can the current pattern of global climate change that we are observing and measuring be explained by natural forces, by natural causes, or is there some other impact that's driving this? And so let's go ahead and start by talking about global climate change. And if you look, this is actually a graph showing the amount of carbon dioxide, which you'll remember is a greenhouse gas, in parts per million over the past 800,000 years. And you can see that dashed line in the middle there, where it says 1950 level. For the past 800,000 years, carbon dioxide has not exceeded those levels. And up on the upper right, you can see that the current level is designated. And right now, as of this month, it is 424.7 parts per million by volume. So, looking at that graph, you can see for the past 800,000 years, we have been under 300 parts per million by volume. And now, as of this month, we're at 424. And this is not even the largest. If you go back, there's the level I'm talking about, the 300 parts per million. If you go back to March of this year, we were at 430.6 parts per million by volume because the amount of carbon dioxide in the atmosphere and how it's being measured, it can fluctuate. It does fluctuate, but not as dramatically to suddenly drop back below 300. We are consistently showing higher concentrations of carbon dioxide in our atmosphere. And so this is the greenhouse gas that, at least to start, we're going to be looking at. And so let's talk about projections and effects of climate change as we're currently interpreting it. Remember that we talked about how we measure different kinds of things that happen on the planet. That's true for the climate. We measure the global climate. We measure the amount of sunlight reaching us. We measure the amount of sea ice that's available on the planet. We measure sea level. We look at wind power. We look at the amount of precipitation in various places around the planet. We look at the amount of snow cover. All of these are things that are being measured. Now, globally, there are any number of temperature stations that are doing this, and in some cases have been doing it for a prolonged period of time. If you look at that color band across the bottom, you'll see that as you move from left to right, you're looking at an increase in years. And if you get over to the right of that line, after about 90, 110, 130 years, you can see that those colors get redder and darker. If you take that information and then look at the map, wherever you're seeing those dark reds or those browns or those blacks, that's where global climate temperature has been measured for the longest period of time, which means in those areas you have a prolonged record of understanding, particularly, hopefully, you can see in the United States there, as well as in Europe and England. There's been a lot of measuring of global temperature over the past century in many cases. And then other newer stations are measuring things as well, and they are more or less supporting or corroborating the data generated from these earlier temperature stations. And again, what we're looking at is greenhouse gas emissions. We're looking at greenhouse gases that may be contributing to some of those temperatures that are being measured. As we discussed, greenhouse gases work because they act as a greenhouse. When solar energy reaches the planet, about 25% of it is absorbed by the atmosphere, another 25% of it is reflected back off into space, which then means about half of the solar energy reaching the Earth's surface actually makes it to the Earth's surface, whether on land or in the ocean. And then as that heat radiates back out as a lower quality energy, because it's lower quality, it's no longer able to make it back out through the atmosphere as easily as it made it in. And so only about 5% of that is reflected out, and much of that gets absorbed into the Earth's atmosphere. And we talked about the impacts of that, how if we didn't have an atmosphere at all, the temperatures variation between night and day would be very extreme. And we talked about the other side of the coin with runaway greenhouse gases on the planet Venus and how they have insanely high temperatures on the surface of Venus, so that we still haven't managed to reliably land landers there or scientific tools there because they melt. So that shows the difference in different kinds of greenhouse gas layers. And what we talked about was that here on Earth, under normal circumstances, all other things being equal, what you have is pretty much the right amount of greenhouse warming in order to enable life to thrive here. And so we measure the amount of greenhouse gases like carbon dioxide that are in the atmosphere. You can actually do this yourself. There are measuring kits that are available that enable you to track the amount of carbon dioxide in the Earth's atmosphere immediately adjacent to you. For those of you who are worried about disease transmission, this is helpful. If you're in a crowded room and this meter is showing high concentrations of carbon dioxide, that means a lot of people are exhaling. And if some of those people are ill, then they could be exhaling contagious elements. So that's one way to actually keep track of what's going on around you. But you can also see what the uh, carbon dioxide or other gas concentration is around you. The same thing is true for larger stations that measure this on a global scale. For example, in Mauna Loa or on Mauna Loa in Hawaii, there is a station that has been measuring the amount of carbon dioxide in the Earth's atmosphere since about 1958. And this is the result of those measurements. And you can see that you've got a red squiggly line and then a black line running through the middle of it. The red squiggly line is seasonal variations. I mentioned earlier that the amount of carbon dioxide can fluctuate, just like it was higher locally in March than it is today. But probably next March it will be back up, and the March after that it will be back up, and so on. But the overall trend is an increasing amount of carbon dioxide in the Earth's atmosphere, measured since 1958 and ongoing today. This curve is known as the Keeling curve, and yes, I will probably test you on that. And what you're looking at here is documented scientific empirical evidence of increasing amounts of a known greenhouse gas in the Earth's atmosphere. This is a more recent version where you're seeing the same squiggle, but it's showing the same sort of thing. It's showing that we're approaching 430 parts per million. Clearly, this didn't take March of 2025 into account, and we'll see what happens next year. But the point being, this is a prolonged measurement of the amount of this greenhouse gas in the Earth's atmosphere. Some of you might be thinking, well, yeah, that's just Hawaii. Maybe Hawaii's just weird. Absolutely not the case, because again, there are multiple measuring stations around the planet, including, as documented here, Barrow, Alaska, Mauna Loa in Hawaii. I just talked about that one, American Samoa, and even down at the South Pole. And in every case, now this starts more recently because these other stations weren't in place all the way back in 1958, but they pick up in 1972, 1973, and 1976 or 77, and then they start measuring the amount of atmospheric carbon dioxide, once again in parts per million by volume. And you can see that All of them document that same rise through time in this particular greenhouse gas. It's not just historic or recent historic times that we can measure in this way. We can also drill ice cores, and we can go to places like Greenland with their Greenland's thick glacial ice. We can go to Antarctica. We can go to the Andes in South America. And in all of those cases, you have glacier ice that has been deposited and has been sitting there at the surface for tens of thousands and hundreds of thousands of years. And so, if you drill ice cores out of that and extract them, what you're going to get when you get the ice, you're also going to get pockets of atmosphere. And so, you can then process these samples and determine the amount of carbon dioxide in the Earth's atmosphere far back in time. That's how graphs like this one and like the one we started the lecture with are produced by measuring how much carbon dioxide is in those cores going back as much as 800,000 years. So that's why we talk about it this way. That's why I mentioned up front that we haven't that we've exceeded that recently. That's how we determine that. It's not just things like the Keeling curve, it's things like ice cores where you can sample them and get that carbon dioxide concentration. We also measure from space. There are satellites that are measuring the amount of various greenhouse gases in the Earth's atmosphere. For example, this is the Greenhouse Gases Observing Satellite. And this is the Orbiting Carbon Observatory 2. And this one, I'll go back. This one is looking at various greenhouse gases. This one is looking specifically at carbon. And it's the Observatory 2 because the Observatory 1 never made it into space. It accidentally and sadly blew up. But this one is actively monitoring carbon in the Earth's atmosphere. And in these cases, they can look at greenhouse gas concentrations not just where we are in the troposphere, because whether it's a personal measuring device or whether it is measuring devices in American Samoa or Mauna Loa or what have you, those are all measuring carbon dioxide in the troposphere. But here you can select uh, other atmospheric layers as well. And so this is how this study is working to track various kinds of greenhouse gases, particularly carbon dioxide, and see what their atmospheric distribution is from the other side, from out in space, rather than from down here on Earth. Now, the fact is that because greenhouse gases like carbon dioxide are greenhouse gases, they can contribute to warming. And so, if you look back again, 800,000 years, you can track and you can see here the sources if you want to look at those. But what you can see here is that temperature in the Earth's past is tracking carbon dioxide levels in the Earth's past. So when you have more carbon dioxide, you have higher global temperatures. When you have somewhat less carbon dioxide, you have lower global temperatures on the average. And we're going to talk about that as well. And so this is an older graph. You can see that we were only, quote unquote, at about 400 parts per million by volume back in 2014, which should give you an idea of how different it is today, given we're up over 420. Now, as we move into winter, this is actually Big Bear, California. This is a few years ago on Christmas Day. This is what it looks like up there. It's very pretty. And some of you might be thinking, wait a minute now, we've had some chilly weather. In fact, we're having chilly weather right now. It's hard to imagine that the planet is getting warmer, that things are warming up when you can have ice and snow like this. I mean, wouldn't this all go away? And this argument has actually been used by politicians. For example, this now former senator from Oklahoma actually brought a snowball onto the floor of Congress, and his argument was since snow forms, global warming or global climate change can't be a thing. That's a very silly argument to make, and it's not supported, but I'm emphasizing this because it has been made and it's still being made by some people today. But there's a couple of things about that. Number one, it confuses the difference between two features. One of them is weather, which is what you look at on a day-to-day basis when, for example, if you're checking your weather app or you're checking the Weather Channel, if anybody still does that, what are you looking for? You're looking for temperatures and you're looking for precipitation. Those are the main things, and that's what weather is temperature and precipitation patterns as well as wind and what have you. And as you probably know, the further ahead you go, the more unreliable those forecasts are. You can forecast what tomorrow is going to be. You can forecast what this weekend is going to be. Once you start looking at next Friday and the Friday after that, things get a little squishy. And that's because weather can change dramatically in a relatively short period of time. So when you're using your weather app, you are aware of this. Whereas climate is long-term weather patterns, which are more stable because they're long-term. They have been observed for up to 30 years or even more. It's the average weather over many years in one specific place, so that you already know that it's probably going to be fairly chilly this January. Now, that doesn't mean we might not have some warm days because it is California and that's the way things work. But it's likely that January and February will be pretty chilly, and it's likely that next year, July and August, will be pretty warm. Now, that's seasonality, but it's also broader trends where you can suggest that August is going to be warm 10 years from now, 20 years from now, 30 years from now. And it's a reasonable guess that that's the case, whereas you can't guess that just a few weeks out. Okay, that's the difference. So somebody says climate is changing and we expect it to be warmer in 20 years or 30 years. That's climate, and it can be estimated, it can be measured, and mathematic models can be constructed to explain what might happen. It's not getting down to nitty-gritty specifics like weather does, where you say the high is going to be 45 degrees and the low is going to be 12 degrees or something like that. It's not that specific. I can't tell you that August 4th, 2047, it's going to be 112 degrees as the high. There's nobody who can make a prediction like that. Um, but I can tell you, and we'll talk about this in a future lecture, I can tell you that it's possible that in that year, on the average, August might be warmer than August next year. Again, part of this is because of seasonality, because the Earth orbits the sun and our seasons change. And that's reliable. I mean, we measure our year by the way the Earth moves around the sun. So we know summers are going to be warmer, winters are going to be cooler because of the angle of the Earth relative to the sun. But that gives us seasons, and that's important because, yes, summer is warmer. Yes, winter is cooler. But look at what's happening over there on the left, where the northern hemisphere, where we live, is tilted towards the sun. It's going to be getting more direct solar energy, and that's why it's warm during the summer. Whereas over on the right, the northern hemisphere is deflected away from the sun. And so the solar energy reaching the northern hemisphere is less intense than during the summer. And so you have cooler temperatures. Now, the important part is that in our summer, in June, when the northern hemisphere is tilted towards the sun, the southern hemisphere is tilted away, which means it's going to have less intense energy. Move to the other side of the graph over there on the right. When we are in our winter, the southern hemisphere is in their summer. That's when they get their hottest temperatures. So when we are having freezing weather, which we frequently have over the past several winters in places like Chicago, New York, and what have you, absolutely frozen temperatures, at the same time on our planet, you have record-breaking temperatures going on in the southern hemisphere in places like Australia. This is from January 2025, January of this year, when we were in winter. These are the temperatures that Australia was facing, 45.8 degrees Celsius. That's how everybody outside of the United States measures temperatures, which would be 114 degrees. At the same time, you had that massive snowfall and that massive ice and snow here in North America. You had blistering temperatures down in South America. And they've had even, excuse me, in the Southern Hemisphere, not South America, in the Southern Hemisphere, particularly Australia. And they have had even warmer temperatures. Back in February of 2024, they reached 121.8 degrees Fahrenheit. In January 22, 123.3 degrees Fahrenheit. And again, this is all in January and February when we are enjoying, so to speak, our winter. Australia is baking in the sunlight. You may remember I talked about this is the Yosemite Valley again, and no, this isn't my picture. I would pay money to drive up there and take pictures like this if I caught it right with beautiful sunlight and clouds and just carpeted in snow from some of those intense storms that struck the Sierras back in 2023. And we've talked about those in the atmospheric rivers that dropped all this snow and how it ended the drought for a short period of time. At the same time that was going on here in California, this is what's going on in the near the equator and in the southern hemisphere. You had massive temperature increases in Thailand and in India. So you would have temperatures up to 118.4 degrees Fahrenheit, absolutely baking in these areas at the same time. I mean, this is April when we are having all those deep storms depositing all that snow. This is what's happening in other parts of the world. And that's why when we talk about climate change and climate and we measure climates, we're talking about global averages. We aren't talking about one specific region or five specific regions. We are averaging the entire planet. This is from earlier this year, and you can see that you're getting up there. Oh, sorry. Happy trigger finger. You're getting up there in the upper 40s and into the 50s in terms of Celsius. The maximum was 48 degrees Celsius, which is amazingly hot. And once again, that's this year. That's what's going on right now. So that's the pattern we're seeing, right? So keep in mind, if I ask you about this on the midterm, if I ask you something like, how can we say the planet is warming when we still have regular snowfall, including right now? That's the answer. The southern hemisphere is in summer when the northern hemisphere is in winter. Let's move on to greenhouse gases. We've talked about some of these before. We've talked about carbon, which makes up 64% of the greenhouse gas budget. Methane, another one, is 19%. Chlorofluorocarbons are at 11%. Nitrogen oxides are at about 6%. And then tropospheric ozone is present in trace amounts. Right now, I'd like to focus on carbon. All right. Carbon um, is the second most common. No, I'm sorry. That's oxygen. Carbon is not huge in the Earth's atmosphere. It's a relatively small percentage of what's in the Earth's atmosphere. Nevertheless, humans, specifically by burning fossil fuels, are pumping another 7 to 8 billion tons of carbon as carbon dioxide into the Earth's atmosphere every year. 7 to 8 billion tons of carbon added to the Earth's atmosphere just by burning fossil fuels every year. Another 1 to 2 billion tons of carbon dioxide are released by cement manufacturing, we talked about that earlier, by forest and grass fires, and by other human activities. So every year we are pumping more and more carbon dioxide into the atmosphere. That's not the whole story. In terms of carbon dioxide, terrestrial ecosystems, land-based ecosystems, can then remove about 3 billion tons of that carbon each year. So we are producing it and putting it there, but all of the living things, the terrestrial ecosystems on the planet, are pulling some of it out. And then oceans are also absorbing up to 2 billion tons of this carbon every year. Nevertheless, that still leaves 3 to 5 billion tons of carbon that are added to the Earth's atmosphere each and every year just by human activities. All right? So keep that in mind. Yes, I will probably test you on these numbers. And that's why we see graphs like this. And this is going from the year one, the year AD one. This isn't going back nearly far enough, or like the 800,000 year graphs I showed earlier, but it's still showing that there's this spike right there where we see an increase in global temperature. It looks like beginning this last millennium, in the year a couple of millennia ago, uh, in the Common Era. Temperatures were declining globally, and then something happened right there. And what happened there was the onset of the Industrial Revolution, where we were continuing more and more and more to consume fossil fuels and produce other things that produce greenhouse gases that then drove the spike in warming that we see there. Now, it has been argued by some people that an increase in carbon dioxide is actually a good thing because, as you know from this class, carbon dioxide is taken in by plants, and then uh, they absorb the carbon dioxide, they make energy or they store energy, which then becomes available for ecosystems, and they release oxygen, which we then inhale and produce carbon dioxide, and it's a nice cycle. And so it's been argued that potentially an increase in carbon dioxide in the atmosphere could lead to improved photosynthesis, improved health of plants, and consequently be an overall net benefit. It turns out that though that's not necessarily the case. There have been studies that have looked at this, and what they see is that carbon dioxide increases, at least in the United States, annual air pollution deaths by about 1,000, and it increases cancer. About 40% additional deaths may be due to ozone, which is also produced as a consequence of an increase in carbon dioxide. So there's the critical information there. An increase in global carbon dioxide is going to lead to a few more deaths among people. It's going to lead to an increase in cancer, and it's going to cause health issues due to related increases in ozone in the troposphere. All right. So keep those things in mind. What also happens is that with the increase in ozone, you can have plant damage. So even if there's more carbon dioxide for them to use, there's also that increase in ozone that's going to cause damage to the tissues of the plants. I should mention that there are some parts of the world, particularly very dry and arid areas, where increases in carbon dioxide have been documented to promote plant health. But that is not true in every situation. That's not true planet-wide. It's very specifically targeted to just a few areas. This is important because we depend on those crops to supply us with food. And so if those crops are being impacted, then if that increase in carbon dioxide is not just hurting people and leading to an increase in cancer in people, but it's also damaging the plants themselves. If we depend on plants as part of our lifestyle, then that's going to be a significant impact. And so this brings us to a subject, and yes, I will test you on that, a subject known as phenology. And phenology is the study of cyclic and seasonal natural phenomena, especially in relation to climate and the life and reproductive cycles of organisms. And the reason I mention this is because plants respond to climatic cues. They respond to temperature, they respond to humidity, and so on when they determine they aren't thinking. They just naturally respond to certain stimuli that leads them to grow and flower and be available for pollinating. And then they depend on other organisms to do that pollinating. And those organisms are also depending on those seasonal cues. So if you have increasing temperatures, and the plants respond differently, or the animals respond differently than the plants do, then you break up that relationship between the plants and their pollinators, which has potentially catastrophic results. Just a note, our area is based on exactly that sort of thing, exactly that sort of relationships. The Inland Empire was renowned for the oranges that it produced, and you can still see that going today. This is actually in my backyard, in the orange tree that my wife and I have in our backyard, where that busy little bee is busy pollinating that plant. If that plant flowers before the bee gets there, or if the bee misreads the climate signal and arrives a little late, then that flower doesn't necessarily get pollinated, or fewer flowers get pollinated, and you can have a reduction in fruit. And if that fruit is of economic benefit, this can have economic impacts as well. So that's a phenological relationship between the orange plant and the pollinators that you see here. And if you monkey with that relationship, all sorts of harm can be a consequence of that. An important point. We've talked about how humans have developed over millions of years, and we talked about how about 10,000 years ago they developed agriculture. And once you have agriculture developing, suddenly human populations take off. They spread even more strongly across the planet. But what that means is we're growing plants, more and more of different cultures, different societies, but as more and more groups of people adopt agriculture as a subsistence base, they're dependent on climatic stability. And that's what you see here. This is more or less the past 10,000 years showing that there's been a relative plateau in terms of global temperature, which ended very recently. And so the plants that we are talking about no longer necessarily have the same patterns, the same processes that they've been used to for over 10,000 years. And the organisms that pollinate those plants are facing the same changes. They're facing the same dramatic changes. So, as we're going to talk about in a future lecture, it has been far warmer in the past than it is now. That's not the point. The point is we have a variety of agricultural subsistence societies and cultures that have been doing it because climate has been relatively stable for the entire period of agriculture up until relatively recently when things have spiked. And so this is uncharted territory. No human beings who use agriculture have faced the global temperature increases that we are facing now. And I've been focused pretty much on the land surface, but the water surface shows the same thing, where we are tracking water temperatures. And what you can see here, once again, that red line is going to be the Keeling curve, and it's going back to 1958. And you can see that same jaggedy line going up that we already talked about. But what's also happening is scientists started measuring temperature in the water and carbon dioxide in the water. And that started in the 1980s. And so what you can see there is that same increase. There's a lot more variability, but you're still seeing that general trend upwards through time. And as you add carbon dioxide to uh, the oceans, you increase the acidity of those oceans. So you can see the pH designated in blue here is going down over the same period that the temperatures are going up, which is demonstrating that it is carbon dioxide that is one of the main drivers of that temperature increase that we see there. Carbon dioxide being added to to the Earth's oceans. And again, I told you that the Earth's oceans are incorporating some of the carbon dioxide that is being pumped into the Earth's atmosphere by human activities. But that reabsorption of that carbon dioxide has consequences. The oceans will end up warmer, they will have less oxygen in them, and they will become more acidic. And so, as things warm, you will have more bleaching, you'll have more toxic algae, you'll impact habitats that need that oxygen, you'll have increased acidification, and you can impact the food sources. Remember, we talked about how half of all meat consumption on the planet is fish and seafood. Well, now here, those organisms that half of humanity depend on to survive are being dramatically impacted by the carbon dioxide that's being absorbed by the ocean, which in turn is being produced by human activities. And so here you have diagrams showing late 1800s relatively low concentrations of atmospheric carbon dioxide and relatively low acidity versus over on the right, projected impacts of increased concentrations of carbon dioxide, higher concentrations in the oceans, and how it's going to impact corals, it's going to impact other marine organisms, prevent them from developing their shells, and so on. Because many of these organisms depend on carbonate ions, carbonates, in order to make the shells that enable them to survive. And if you're adding carbon dioxide to the ocean, then you're going to have uh, fewer of those carbonate ions, which is going to slow down the process of calcification and shell forming and so forth. That's all been carbon. We can go ahead and talk about methane as well. Methane is the second most abundant greenhouse gas in the Earth's atmosphere after carbon dioxide. It makes up about 16% of global greenhouse gas emissions, but it's more than 28 more times more potent as a greenhouse gas than carbon dioxide is. It's shorter lived in the atmosphere, though, meaning it only lasts in the atmosphere about 12 years. And so it's much more potent, but it doesn't stay in the atmosphere as long. And one of the main sources of methane gets back to what we do, how we impact the planet, because of the number of organisms that we are growing, that we depend on for our meat, and the fact that they produce methane at both ends. They produce methane by outgassing out the back as well as by burping. And then that methane makes it into the atmosphere where it stays there. And after about 12 years, it breaks down into carbon dioxide and water, which then feeds the photosynthetic pathway, which then is consumed by the cow, and you start the whole cycle all over again. And so that's why this methane cycle is going to continue. But the more of these organisms you have, the more that you're going to add that greenhouse gas to the Earth's atmosphere. And it's going to be in there for about 12 years. That's oxidation right there, which we talked about before. Here's a more detailed thing. It's the methane cycle, and this includes some of those domestic animals, those primary producers, as just one component of it. There's any number of ways that we are producing methane and pumping it into the Earth's atmosphere, so be aware of these as well. Now, notice that in terms of global anthropogenic or human-caused methane emissions as of 2020, digestion by ruminants. Ruminants would be things like cattle. They ruminate. That's how they get that name. They have a rumen where they do digesting. And their fermentation in their guts of the food they're eating is producing over a quarter of all of the anthropogenic methane in the Earth's atmosphere, more than any other human activity. And so here you can see sources from global methane emissions, and you can see there you've got emissions from human activities at 60% of methane emissions, and then emissions from nature are only about 40%. So not only are humans contributing methane to the Earth's atmosphere, where it acts as a greenhouse gas, but they are contributing the largest percentage of methane to the Earth's atmosphere. So when the final runs around, please be aware of that. Concentration of methane in the Earth's atmosphere has more than doubled over the past 200 years because of human activities, because of human lifestyles. This increase is responsible for 20 to 30% of climate warming since the Industrial Revolution way back in 1750. And again, you can see that here, where you can see the same trends as what we're seeing once again. There's your Keeling curve. In this case, it's only going back to 2005. So it's the top end of the Keeling curve, but that's in green. That's CO2 being measured. And then the methane is tracking along the same trend. It is also increasing in its concentrations. There is still methane being pumped into the Earth's atmosphere, and even though it eventually breaks down due to oxidation, nevertheless, it is still increasing over time. So, what are the consequences of this? Well, We've talked about some of them. Global temperatures continuing to rise. Sea level has the potential to rise as much as 1 to 8 feet, depending on where you are on the planet by the year 2100. Oceans, as we just discussed, will become increasingly acidic. Growing seasons will potentially lengthen and change. Frost-free seasons will also lengthen because the temperatures are increasing. Precipitation patterns will change because that's driven in part by temperature and air patterns. It's likely that more droughts and heat waves will occur. Hurricanes will increase in strength and intensity, as may very well be happening now. And at some point, eventually, the Arctic is expected to be ice-free. And so here you have various ranges, various things that can be done to project what might happen. This is from just last year or the year before, where it talks about aiming for reducing greenhouse gases, reducing temperatures below a certain threshold based on human activities and actions that humans can take. We're going to talk about this more. I'm just touching on it here briefly, but you can see that current policies over there on the right show a big increase in temperatures, whereas if we move towards other commitments like net zero commitments, we can reduce these greenhouse gas concentrations and consequently we can reduce the warming through time. Now, we're talking about a lot of this. Let's also talk about snowfall. Let's talk about some of the ice and snow. We've talked about it locally. I gave you this diagram earlier, and this is what the Sierras looked like back in April. And again, we depend on the Sierras, both on the east and the west, depending on the aqueduct. We depend on that for the water that's coming down to us. We need that water in order to survive, to support the large numbers of people that we have here in the various big cities in Southern California. We also need it for agriculture in places like the Central Valley. So if temperatures are reducing that snowfall, temperatures then are going to reduce the amount of fresh water available, which is going to have massive impacts on our agriculture, on our way of life, on simply the availability of drinking water. It's also going to have an impact on plants, and this has been documented. Probably, if you've gone driving through our local mountains, you've seen any number of essentially dead conifers and pine trees, and that's because even though they can get by with limited amounts of water, they aren't getting enough. And so they're weakened, and in their weakened state, either they die from lack of water or they die because they're impacted by pests, in this case, the bark beetle, that will come in and take advantage of the tree's weakened state and start consuming the bark, which further impacts the trees. Bark beetles like this one are well known locally and unfortunately are having a huge impact locally. So trees might have been able to come back in some cases, but then once they're infested with bark beetles, they're pretty much done. And it would be an enormous amount of effort to try and control this because these things are so prevalent where you have dried out, desiccated trees. And what that damage leads to, as you can probably guess, is an increase in, with dead trees, that's fuel. And so that leads to an increase in wildfires, which I'm sure you're aware of, that we have had increasingly large fires. We have fire season every year. And even though a lot of these areas, as we discussed in our biome lecture, are wildfire adapted, nevertheless, they don't have the resistance if they've died or if they've been destroyed by bark beetles, and suddenly they just become wood to burn. And so that's a big part of what's been going on with our fires locally. Getting back to snow, this is impacted by increasing temperatures as well. We have snow that is melting on the planet, and what happens to snow melt? It goes in the water, it goes in the oceans. And that's important to keep in mind because what you're looking at here is areas, and this is just Florida as an example, where what you're looking at here is elevation of land in Florida. So where you see that it's red, that's land that is less than a meter or less than 3 feet above sea level. So if sea level rises even a little bit, it's going to impact those communities. And as you may know, you're looking at some very wealthy communities down there. There's an enormous amount of money there, particularly along the coast, that would be impacted by even a slight increase, an average increase in sea level, but in sea levels, in seawater levels. That's me picking on Florida, but I don't want you to get out of this thinking that it's just Florida, because if you go up to places in California like San Francisco, there are some low-lying areas as well. So if sea level rises even a little bit, there's going to be any number of coastal areas in the San Francisco Bay Area that are going to be impacted by those increases in sea level. And if San Francisco is too far away for you to worry about, we can also look at it locally as well, where if sea levels rise, as they're projected to do, then you might see inundations. This doesn't mean these areas will be permanently underwater, but it does mean that as sea levels rise, they will increasingly be impacted ever further inland. This is an estimate from Climate Central, what the situation might be by the year 2030. And then here's what it might be in the year 2100. And when you think about all the people living in these areas, you can see that this would be a dramatic impact on our way of living, on the people that we know, family members, people that we're friends with, live in these areas and are going to be impacted over time by these changes. Which brings us back to, are the temperatures still increasing? And this is showing fluctuations from January through December for a variety of years. You've got 1940 to 1925, you've got the 1991 to 2020 averages, and then you've got so far as of the 2nd of November, you've got more recent times. The warmest year on record was I'm drawing a blank. I think it was 2024. And then the next warmest year was 2023. I'm not going to test you on that yet, but we're going to talk about it in the next lecture. And so it's looking like 2025 so far is keeping pace with those two warmest years on record. That's what we're seeing here. That's also what we're seeing in the ocean, where pretty much, particularly in the ocean and particularly in the early part of this year, temperatures were well above average and in many cases exceeded some of the other warmest years on record. So this is what's going on right now with our temperatures. We are in November, the year is almost over, and based on projections and interpretations of what might happen, the predicted final value for 2025 is that it will be the second or third warmest year on record after 2023 and 2024. So that's 3 years of intense heat in a row. And we're going to talk about that pattern more in the next lecture. So with that, I'm going to go ahead and end it here. The next lecture might be a little delayed, and I apologize for that, but I'll do my best to get it out to you as quickly as possible. In the interim, have a good day, a good evening, and if you have any questions, please feel free to reach out. And we'll talk to you soon. Thank you very much. Have a great one.